Hey guys, in this lesson we are going to be studying the work-energy relationship. This is probably the only lesson in the unit that you might consider challenging and that you might think you would need to study before the quiz. This probably won't introduce any equations that are brand new to you, but we're going to be linking previously unlinked equations. So be prepared to think creatively and to work hard. So let's get started. The bookwork associated with this lesson is right here. If you don't mind copying down this assignment description as the first page in your classwork page for this notes, that would be great. And then copy down this aim. What's the relationship between work and energy? And after that, I do want you to sketch this very dramatic cartoon, and also this one, and the questions associated. We'll answer them in class. Okay, so the work-energy relationship. Basically, it's getting at this idea that if you are doing work on an object, like a mass right here, if I do some amount of work on it, then I'm going to be giving the object a certain amount of energy, and that amount of work and that amount of energy are equal. So you can ask it in different ways. Like, for instance, I could say that you have this mass and we raise it to this height, and then you take the mass and the height and you take gravity, 9.81, you multiply them together, and then that would be the potential energy of the box when it's up here on top of the table. The potential energy that that box has is obviously, it would have come from work. So I could ask you, what's the work that's been done on the box, or what's the work that's been done against gravity when it's up here on top of the table versus down here at the bottom. So just know that potential energy and work are very related, and that's pretty much what's going on this slide. When work done against a force is independent of the path taken, meaning like this potential energy stuff, like it doesn't matter whether it takes path A where it goes all the way up and then comes down a little, or whether it does diagonal stuff or all horizontal, none of that matters. And that's because we call this kind of force a conservative force. So conservative forces are ones where the path taken doesn't matter for the amount of energy gained or lost. So gravity is an example of that. Elastic force of a spring is also a conservative force. Okay, so there are non-conservative forces, and one of them that's going to come up, every now and then is friction. So friction has the ability to actually really affect the amount of energy that's gained or lost as a result of the path taken. Like, for instance, if you have two different choices to get a 10-kilogram mass to the top of a table, but one of them is like a shorter distance and the other one's like a longer distance, and assuming that we're allowing for friction, meaning that there's friction along this plane and there's friction along this plane, then what's going to happen is this one's going to have less friction because it has a shorter distance over which the friction can occur. So two reasons that I could state that make that true is that as you move along incline B, you have a different scenario along incline A because incline B is longer, right? So the work that's done against friction is going to be equal to the frictional force multiplied by distance. So essentially what I'm saying is in incline B, the distance is larger, so that means that the work done against friction is larger. And there's another reason for this as well. When you are looking at incline B, you can judge how much frictional force there will be based partially on the normal force. And the normal force for this guy is going to be larger than the normal force for this dude. And that has to do with the angle theta at which the block is to the plane. So basically, since this guy has more of a horizontal approach than incline A, then the normal force is larger, and therefore the frictional force is larger. So a second reason why incline B would use more work and more energy is because the normal force is larger and the frictional force is larger, so with a larger FF you'll get a larger workforce. Okay, so conservation of energy. If you have a closed system, and a closed system basically just means that you're in this like system of things that it can't lose energy and no energy can come in. So you whatever is there is has always been there and won't leave. Basically, that's the ideal system to study the law of conservation. The law of conservation says that matter, energy, charge, momentum, all kinds of stuff can't be created or destroyed, or it has to be the same both before and after any change occurs. An example of this is Newton's cradle. You guys have probably seen these on TV. I have a broken one in my room. You guys can take a look at it. But basically, it's just a box that has some weights, some nice metal weights that are attached by strings, and then they can go back and forth and hit each other. But one of the things that's surprising about it is that, like, if you lift two up, then two will go off the other side when they're collided with. If you only lift one up, then only one will come off the other side. So I guess that's what I'm getting at here. If you have two spheres falling, you'll have two spheres rising. If you have one sphere falling, you'll have one sphere rising. And the explanation for that has to do with that energy has to be conserved. So if two spheres fall, you have twice as much energy, which is going to need to go into the other two spheres as they rise. So since the energy of the falling spheres is the energy of the rising spheres, then it should not be surprising that if you lift two spheres from the left, that upon collision, two spheres from the right would rise. Ideal mechanical systems are ones where you have this like perfect conversion of potential energy into kinetic energy. An example of a mechanical system that could be considered ideal is a simple pendulum. We've talked about this in previous lessons, but basically, if you raise a pendulum above a height, you're giving it its like maximum potential energy because it has its like largest height when it's up here. And as it falls, it's going to be losing potential energy because it's losing height. But ideal mechanical systems would not break the law of conservation. So you can't just be losing potential energy. That energy needs to be going somewhere. And in this case, the energy that's being lost from potential is being converted directly to kinetic energy. So this is another example of energy being conserved, by the way. But we have this potential energy being lost with kinetic energy being gained to the point where you get to the lowest height, and at the lowest height, you're going to have no potential energy, at least relative to the original. And the kinetic energy will be at its maximum because guess what? All of the kinetic energy came from the potential energy. So as the potential energy bottoms out with nothing left, the kinetic energy has all of that energy. So now it's going to be at a maximum. But as you know, a pendulum will continue to swing, right? So as it comes back up on the other side, it's going to be gradually converting its kinetic energy to potential energy so that the potential energy will be back at a maximum up here, and the kinetic energy will be at its own minimum down up here as well. So what you have basically is just like these two buckets of energy that are constantly pouring back and forth into each other. At the top, the bucket is full for potential and it's empty for kinetic, but at the bottom, that full bucket of potential has been poured into kinetic so that the potential energy bucket is empty and the kinetic energy bucket is full. It's just one way to think about it. So in this slide, I want to focus a little more on the non-ideal mechanical systems, the ones where energy is sort of lost in unexpected ways to the environment. Friction is probably our number one culprit for the pathway that energy will take when it's not creating an ideal mechanical system. So, for instance, if you have a simple pendulum, just swinging a simple pendulum actually does not usually result in an ideal mechanical system because the friction between the string and the anchor point will produce a bit of loss of energy, and also friction of air resistance produces loss of energy. So basically, in short, as you swing a pendulum, you can be confident that it will not always rise to the same height that you would expect it to rise to from the original. And the reason for that is because of the loss of energy as it goes. If you drop a piece of paper to the ground from some height, it'll have more potential energy with respect to the ground than it will have kinetic energy at the instant it reaches the ground. Now, in an ideal mechanical system, this kinetic energy and the potential energy would be equal, but in the real world, we know that that piece of paper is going to experience drag from air resistance, and it will lose energy to friction as a result. Lastly, a lead sphere dropped from a height onto a steel surface would not bounce. All of its gravitational potential energy, it would be converted to kinetic energy by the time it gets to the bottom. Very little would be lost to air resistance. However, since lead is a really soft material, when it hits that steel at the bottom, it's going to absorb the energy as internal energy. So it'll basically just absorb all of this heat as it strikes the steel at the bottom. All right, I have one video to show you, and that is going to be what would happen if you take two steel balls and you smash them with a piece of paper in between them.
What's up, everybody? Welcome back to my laboratory where safety is number one priority. And today we're gonna do a cool experiment with the steel balls. Let's check this out. So what I'm gonna do is pull off a piece of paper, then I'm gonna fold it just like that and stand it up. Then I'm gonna grab these two steel balls and I'm gonna smash them on each other right here. Let's see what happens. We got a hole, and it actually burned a hole too. And you can actually smells like burnt paper. This is so cool. And you don't even have to heat it hard, but if I heat it hard, it burns to a hole even bigger. Isn't it insane? Two steel balls like that produce so much energy that is produce heat. Pretty insane. So, and if I heat the paper, that heat is powerful enough to burn through a hole in it. You definitely can smell the smoke. So what happened is the steel balls, when they moving, they got energy, and when they hit each other, we got different energy. It's producing a lot of heat, and boom, it's burning a hole in the paper. Try it yourself, be careful, and I'll see you next time.
So as we sort of slam those two steel balls together, all of their kinetic energy was converted into heat because they didn't convert into anything else. It was sound and heat basically, and that amazing amount of heat burned the paper. All right, so here's an equation for you. It basically just says that the total energy of a system is going to be the sum of all the potential and the kinetic and the heat or internal energy that is in the system. So that's basically it. It's just saying that energy is conserved, and that if you add up all of the energies, it'll equal the total. We can use this equation creatively within this unit, sort of similarly to the way we would use the equation P before is P after, where it almost means nothing, but at the same time it means everything. So we're going to use it to say that all kinds of things are equal and transferable. Here's an example. We have a basketball player who weighs 600 newtons, and she jumps half a meter vertically off the floor. Let's calculate her kinetic energy just before hitting the floor. So I got a diagram to start us out. She's falling, and she has potential energy from where she is. We're going to calculate the kinetic energy, because what I'm going to say here is that the potential energy that she has, it is equal to, and it also becomes her kinetic energy. So I'm going to solve for her potential energy, but that will be my answer for the kinetic energy question. So her kinetic energy is going to be equal to, in this case, her mgh, or her mg change in h. This is kind of an odd thing to look at, but it's because PE and KE are equal. So so the KE is going to be her mass times gravity, which is 600, that's her weight. and her height was half a meter, excuse me. So that means that her kinetic energy is 300, let's see, joules. So 300 joules is going to be the kinetic energy she has when she reaches the ground. All right, let's answer some conceptual questions. As an object falls freely in a vacuum, what happens to its potential energy? If it's falling, its potential energy is going to be decreasing as it falls freely. But its kinetic energy would be increasing. And those two things are related. It's because the potential energy of that object is equal to and is becoming the kinetic energy. The internal energy of the object, nothing is going to be changing. There's going to be no change here. And the reason why is because we're in a vacuum. Now, if we were not in a vacuum, if there were air and it were providing some kind of drag and air resistance and friction, then the internal energy would be increasing. But as long as you're in a vacuum and there's no friction, then there's no change in the internal energy. The total mechanical energy is also going to be constant for sure. Constant because the total mechanical energy never changes, and it's described by this equation up here, and it's just not going to change. What can change is that the PE can go down while the KE goes up, and the Q stays constant, and then that'll keep the ET the same. So just to highlight that point, I'm going to toss in some numbers here. Let's say that she has her original, what was it, would have been 300 joules of potential energy. And originally at the top of her flight, she would have had 0 joules of kinetic energy, and her internal energy would also be 0. So that means that the total energy is 300. Now, as she falls, she converts all of her potential energy into kinetic energy, so that at the bottom of her flight, she has 0 potential energy joules. But all of those joules would be converted into kinetic energy joules, assuming that none of the joules were lost to Q, which is heat, which means that the total is still 300. So that's why, in short, the total mechanical energy of the system always stays constant, even though the potential energy and the kinetic energy and the internal energy can change. And with that, we have finally reached our pair up. Please copy down these particular questions. Oh, just kidding. Don't copy these down. I'll have a handout for you. These will be on the handout as well. And these summary questions, however, please do copy these down. Don't answer them, though. And we'll answer them when I see you guys. Thanks for watching, and have a great day.